Hello, welcome to another Stat 432 video. This will be simultaneously a review of the last two videos, but then also doing the things from those videos inside R. This is my second take at this video, so I'm going to try to not skip over things that I've already said, since I already said them once. Anyway, so I have my notes here, which is the code I want to go over. Some of it, I never know where to point. Anyway, some of it is already on the screen. Some of it is not. All of it will be in the book in some fashion. It might not be exactly what you see here, but it'll be the things you need, to be able to repeat this process. Okay. So, because again, I want to type it in front of you so you can kind of see along the way, both me making mistakes and how I sort of actually input things. And some of it, but the stuff you're already going to see, it's getting repetitive, so we don't need to do it again. Let's start with some packages. Actually, let's start with making me a little bit smaller so we can see what happens to the environment as well. How about right there? Okay, cool. All right, packages. Tibble, you know what that does. It's for making tibbles. We're going to use some tibbles. ggplot2, that's for graphing. I'm going to use it. You don't need to use it. You don't necessarily need to know how to use it. It's not a bad thing to learn, but it's not really what we're here for in this class, although it can be useful. Rpart, fit and decision trees. You knew that already, but we're going to use it for classification. Rpart plot for making fancy plots of decision trees, but you knew that already. Caret, big machine learning package, but we're going to use it for one function, KNN3 in this case. Palmer penguins is a cool data set. It's about penguins. We'll have a look at that at the end of this video. And MLBench is what we're going to use right now to make some data. MLBench is a package for benchmarking machine learning methods, and it has a lot of nice ways to simulate data that is useful for machine learning. Let's do that right now. Okay, so I'm going to set a seed so the results don't scare me, or surprise me, I should say. Okay, so this code here simulates some data. Not super important, but that's what it does. Let's do it. Wow, we're off to a good start. I didn't load any packages. I'm going to rerun the seed because every now and again, packages change the random state, and that's a problem. But anyway, that's for a different time, and hopefully we never see that happen. But that's why I like to load packages at the start. Okay, simulate the data. Great. We see that it affects our environment. Let's test train split the data. You've seen this code before. It's not exciting. Estimation, validation, split the data. You've seen that code. It's not exciting. Let's have a look at the data. Cool. So what do we have here? Two feature variables, x1, x2. They're a bunch of numbers. Great. Not super worried about that yet. Classes. This is going to be our response variable. When we see 1, 2, 2, 1, 3, and you might say, hey, wait a minute. Those are numbers. I thought we were doing classification. Why, yes, they are numbers, but there's only 3 of them, and they're stored as a factor variable, so those are categories. Okay, so first thing I'm going to do is do a bunch of visualization, and the code for that, not important. Go back and have a look if you want, but it's a bunch of details that aren't important to us right now. But let's have a look at it. So, going to start with the bottom left here. So what this is, it's a histogram of the x1 variable. It's actually 3 histograms of the x1 variable. In red when y is 2, in green when y is 3, and in gray when y is 1. Okay, and what do we see here? Well, we see there's a lot of overlap where all 3 histograms are sort of overlaid and you can't even really see what's going on. But I can look at, say, well, let's take a look at a value of negative 2.5. Anything to the left of that is less than it, there's really only red over here. So that means that, like, well, hey, we'd probably have a good time classifying, observations that have an x value less than negative 2.5. Sort of similarly, above positive 2.5, there's not any red. There's a little bit of green, mostly gray. So in that area, we'd want to classify to gray. We'd be wrong occasionally, but we're doing good. So that tells us that this variable is useful for prediction or classification in this sense. You can make a similar argument over here for x2, but I want to go up here to what is called a density plot. So I'm estimating density curves instead of plotting histograms. It's effectively doing the same thing, but just smoother. We might talk about this later on in the class, but for now, I think you get the general notion. It's just easier to see, in my opinion. So like that argument I just made about negative 2.5, well, it holds up here too. And we see there's massive overlap, but a little bit of separation. So both these variables taken individually, we think could be useful for a prediction. Well, but let's visualize them together, which I will do here. And we will zoom that in. Okay, so we saw there was a ton of overlap when we looked at both variables in one dimension. But if we look at them in two dimensions, we see that these sort of blobs of the various colors sort of separate a little bit more. They're not separated, but they separate more. I realize I'm missing a legend here, but black is 1, red is 2, green is 3. I forget what 3 and 4, what 4, 3, 4, and 5 are, but 3 is green. These are like really standard things inside of R. That's just how R deals with colors. That's how I'm plotting these colors. But a note here that I'm super excited about, which is that, and I guess anyone who's been using R for as long as me might be a little thrown off by this anyway, which is that these colors here are slightly different than what they normally are, meaning the red and the green have been dulled a little bit from their sort of original colors. And I think this is a much nicer plot to look at. But anyway, so we kind of see in this region, it's pretty obviously classified as red. Down here, pretty obviously should be green. Up here, pretty obviously should be black. In the middle here, who knows? But yeah, so I would say that this tells us we're going to be successful classifying. We just won't be perfect classifying. Okay, what do I want to do? I want to fit a KNN model. So let's do that. What did I call it? That's okay. So mod KNN. So we're going to use a KNN3 function from the caret package. We're going to say classes is the response variable. The other two are features. I'm just going to, for now, use the train data, but we'll go and tune it later. But for now, I'm just going to pick an arbitrary K, which is 10, for no reason other than I felt like it. And I wanted to show the use of that parameter. And if we look at the output, it looks pretty similar to what we saw when we used regression. It would have only said this, but it also gives us a little bit of summary of the data we used, which there was 265 1s, 289 2s, and 246 3s. Okay, so now what I want to do is I want to make predictions, that is classifications, with a new observation. And that new observation I'm going to start with, we'll put it at like 0, 0. Yeah? So I'm going to call it new obs is a data.frame where x.1 is 0 and x.2 is also 0. Now let's say I want to predict with mod underscore KNN that new obs. Cool. All right, what do we have here? So we see that this output has 3 columns. A column for 1, a column for 2, a column for 3. Hey, those are the categories. But then it gives us these numbers, and the first thing you should notice is that they add up to 1. Why is that? Because it's a probability distribution, or at least an estimation of one. So that means that of the 10 nearest neighbors, 50% of them were red, 50% were black, 30% were red, 20% were green, and then again, we're talking about right here, so that seems reasonable. Cool. So what's actually happening here is there's another argument to this function called type, and we're using type equals prob, but that's the default, so we didn't have to type that, but I just want to note that that is that because I could instead, do class, and that outputs 1. In other words, it outputs the category that corresponds to the highest probability. Cool, that's useful. All right, for fun, let's try some other regions. Let's try the point -2, 2. Okay, so here we see there's a 10% probability that it's a 1 that is black, and a 90% probability that is a 2 that is red. Makes perfect sense. So we would classify to 2 or red. Let's maybe go, let's go crazy for a second. Let's do negative, I don't know, 200. All red. Because like these things here are the nearest neighbors, even though we're like, off the charts in terms of where we're looking there. Something to keep in mind. Let's for fun just do, I don't know, 2, 2. That looks like it's a heavy black region. All the neighbors are black there, actually. This red one and this red one weren't actually close enough. Maybe we'll come down to 2, negative 2. That's a heavy green region. That is 3. All 3s. Brick 3. Cool. So that's K nearest neighbors. We'll come back and talk about how you would tune K, but you already know how to do that. You just haven't seen me do it, but I think you know how to do it. Okay. Tree model. Cool. What do we change here? Well, I'm going to change the name. I'm going to change this to R part. And K is not an argument to R part, but min split is. And I'm going to set it to be 5. No reason other than I wanted to change something. Okay. And then let's do this again. Okay, so that's fine. We need to change this to this and this to this. Okay, so at where were we looking here? It's 2, negative 2. So that's 2, negative 2. So right about here. Wait, no. Sorry, 2, negative 2. That's like here, right? So we see that there's a low probability that it's 1 that is black, another low probability that it is 2 that is red, and a high probability that it's green, 3. That makes sense for right here. But and then we could change these numbers and we'd get different probabilities and classifications. If we do the classification here, it's 3. But let's visualize this. So I'm going to create 2 plots simultaneously. Bear with me. Okay. So the left is the data and a visualization of it that you've already seen. The right is a visualization of the tree that we just fit. And so what I want to talk about is going down the left side of the tree, just for example. So the left side of the tree, and again, root node here, terminal nodes down here, also called leaves of the tree, internal nodes here. All right, so if we start at the root node, which includes all the data here, it says we want x1 above negative 0.34, which is basically 0. So that means we want stuff on this side of the plot. Okay, and that puts us down into here. And then if we say, well, we also want x2 to be bigger than negative 0.4, which is pretty close to 0. So that means we're basically up here in this region here. Okay. So what do we have down here? This 1. Well, that's the majority class in that region, which is 1, which is black. I've colored the cells here accordingly, so you can see that. What are these 3 numbers here? 0.75, 0.12, 0.13. Well, those are the proportions of 1s, 2s, and 3s, blacks, reds, and greens in there. So that's our estimate of the conditional probability of classes given an x1, x2 up in this region. And then this 36% of the data we use to train this method is inside of there. Okay. So what I want to do is sort of go back and verify that a bit. So like, let's say we picked a point up in here. So like, I don't know, 3, 3, that should get me in that region. And I return those probabilities, 0.75, 0.75, 0.12, 0.12, 0.13 with some rounding, 0.13. Hey, cool. So that tree basically summarizes all of the potential probabilities that we'd get here. There's only 4 terminal nodes here. I really should figure out a way to plot them here. I've seen it. I've done it before. It's hard to do, though, so it's a little bit annoying. But roughly, like, this node here is like this quadrant up here, which makes a lot of sense. And you should maybe go down this tree yourself, see where the regions are, see where the points are, see what the estimations are. And I think you'll see that it all sort of shakes out. Okay. Before we go on to calculating metrics and things, I'm going to do something bad. I'm going to go back up here and make this a numeric variable and plot this. And then I'm going to do rpart.plot that thing. Huh. That's a regression tree, which we've seen before. So this is why you want your response variable to be a factor. Because again, if we look at train $ classes, I mean, it's 1, 2s, and 3s, but it's a factor. If I do as.numeric, well, two things. Well, it's 1, 2s, and 3s, but it's not a factor. So now it's pretending it's numbers, so we're doing regression. So that's something you really need to be aware of. But like I said, if you just keep it as a factor, you won't have any problems. Okay, moving on. Let's reset my plotting. All right, so I want to calculate, say things like, I'm going to calculate the test misclassification for k nearest neighbors. So I'm going to check my notes here just to make sure I didn't forget anything. Right. So the first thing I want to do is write a function. So I'll call it calc misclass, and it'll be a function. We'll take two arguments, the actual values and the predicted values. This is sounding familiar, right? So we're going to look at when the actual is equal to the predicted, and we want the mean of that. Okay. There's kind of a lot going on here, but so we're checking if the vector of actual values is equal to the predicted values, and then we're getting the proportion of times that's true. Oh, misclass. I want them to be not equal. Okay, cool. I think you should hopefully see how to very quickly change this function to be accuracy instead of misclassification. Hint, I accidentally already did it, but then I fixed it. Okay. All right, so let's calculate a test metric. So I'm just going to steal this real quick. So I've already fit to the training data. So now I'm going to say calculate the misclass when the actual value is the test data $ classes, and the predicted is what? So I need to do predict. No, not predicted. Whoa, that's not a helpful autocomplete. Predict on mod KNN on the test data. And remember, if I do this, it's going to give me this. But I'm comparing to this. So I had better do something like this. Much better. Compare. So in the test data, about 20% of the time, we're making the wrong classification. Cool. Just to show what this would look like. So here is the actual values. Here are the predicted values. Here's what happens when I check that equality. So this is true when they're not equal. This is false when they are equal. And then when I do mean on that, it's going to coerce the falses to be 0, the trues to be 1. This is a really common idiom. We've seen it already before. Except I keep doing the wrong thing. Okay, there we go. Cool. That's some weird rounding, but that's for another day. Okay. Yeah, that's really weird. All right. All right, so now I want to tune it. So I've just been doing this one value of k already on the training data set. I should probably instead, I should fit to the estimation data and then try a bunch of k's. Okay, so checking my notes. All right, so I want to set up some k values that we're going to try here. And I'm just going to randomly, I mean, not so randomly, there's a pattern here, but I'm typing it like that. Okay, so we're going to try these different values of k. So because I know I'm going to do this a bunch of times, I'm going to write a function and then use the apply type function. So I'm going to call this function fit KNN to the estimation data. It's a function. No. Function of k. And what I'm going to do, I'm going to do KNN 3 classes tilde dot comma data equals estimation, and k is k. So this k is now being passed to this k. All right, so now let's fit those models. So I think if I do fit KNN est and do like 5, we see that, okay, good, it's working. That fits KNN with 5 there. Okay, but so now what I want to do is I want to apply, I want to try an lapply first, this function to the values of k. That looks good. So I'm going to call this knn mods. All right, cool. So now I want to make predictions with that. And I want to make predictions on the validation data. So I'm going to try an lapply. So now I want to apply to the models the function predict, and I need to tell it that the new data is val. Aha. But this is no good, because for each model, it's outputting a bunch of predicted probabilities. So like, this is using the 9th model, which is KNN of 17. So this is the estimated conditional probability that y is 1, 2, and 3 for the first observation in the validation data set, and so on and so forth. What I really want is, instead of this, because this one is highest, I want a 1 right here. So I also need to tell it that the type should be not probability, but class. And now I see a 1 there. Much better. I'll call this, I want to keep all my variable names, KNN preds, we'll say. Okay, cool. So now I want to calculate all of the validation misclassifications. So I'm going to do an lapply at first, but I have a feeling I'm going to change that. So I want to do KNN preds. I feel like they changed some of the autocomplete on me here. And then the function I want to do is calc misclass, and the actual values are going to be the validation classes. Okay, that looks good, but I don't want it to be a list. So we'll do that, and then I'm going to call this KNN misclass. Okay, and then looking at these results, I realized there's probably a seed that I didn't set somewhere that now this is not what I want, but oh well. Okay, I want to plot this to sort of see what's going on. So I'm going to do plot k val KNN misclass. Okay, a couple things there. Let's make this a little prettier. So let's do, I like that plot character better. We'll do type is both. We'll add a little grid. Let's see what that looks like. Okay, that's better. So I'm actually going to do something. So we kind of see the curve that we expect here, and so we like this value here, but I'm worried that it's going down again. So what I'm going to do, because my code is so nice, I'm gonna throw in some more values here and hope that when I rerun this now, it's gonna go up. Oh no. Oh, there are two things happening here, and I'm glad that I did this. I think. Let's run that again. Do we notice that it's changing? It's changing. That's worrying. And it's getting better later on. Like, if I had only looked to here, I would have been fine. And I might cheat and do that for the purpose of this video, but it's changing. Why is it changing? Because of ties. So, with 13 nearest neighbors and 3 categories, you could get 6, 6, and 1. And then when it goes to predict, bad things happen. And I actually want to check something. Yeah, so there's no way around that. That's just how it works. So there is this argument called use all. That's not the kind of tie we're talking about. If there were ties and distances, and then like if we were doing k nearest neighbors with 10, and the 10th and 11th observation both have the same distance, this tells us how to avoid that tie. But with the ties that we're talking about, like it's 6, 6, 1 when there's 13 neighbors, that it doesn't do. So what I should really do is I should, before I make, well, I'm just going to set a seed at the top of this again. 342. Let's do set dot. Let's do set seed. Okay, so now whatever I get here is going to be what I consider. And I'm realizing now what I should really just do is do something like this. Let's just try a bunch. Okay, so, and I can do that because of what we've done here. Wow, so it really likes. I'm gonna go even further. 100 should do it. Wow, let's do this. Let's do a sequence from 1 to 101 by 2, just so there's not so many. So we don't have to get super specific here. Okay, fine. And it looks to me like this would be the best. So we want to say something like which dot min knn underscore misclass. So the 28th k value that we tried was the best one, which would be that value of k. So that's a value of k we would take and then fit to the training data and then get test misclassification. But in the interest of, I think we've kind of seen that already, you can try that for yourself. So a few things we've noticed here. KNN making predictions can be a little too variable. I'm now silently freaking out in the back of my head, wondering if this will be a problem on the quiz, but I'm pretty sure not, because I'm pretty sure I only did binary situations so that you cannot encounter those ties, because I also used odd values of k. Spent a lot of time dealing with this issue in the past. Okay, so I'm pretty sure that's true. Anyway, if it's not, we'll come up with a solution, which will just be to tell you to set another seed, but it'll be fine. Okay, something else to mention here. There's another tie that could happen here, which is that we could get, like, I think probably is happening here, we could get two values of k that produce the same misclassification. And that could happen with the lowest one as well. So two values of k get the lowest misclassification. The question is, which one do you use then? The answer is the one that is the least flexible model, because that's least likely to be overfitting. So all other things being equal, always pick the simplest model. So if two models both achieve the lowest validation misclassification, go with the one that is a less flexible model. Okay, cool. So note to self, check for binary examples, which I'm pretty sure we already did. Check for odd k. This didn't come up in our testing, so it shouldn't be a problem. Because I thought about this. Except not with this little bit of code. All right, cool. So that was some boring simulated data. Let's have a look at some penguins. So this data comes from the Palmer Penguins package, which I want to look at real quick. So Palmer Penguins. It has this cute little hex sticker here with, I think, the 3 different types of penguins in this data set. If we look at this here, which I actually already had open, but this is a quick way to bring this up. So what this data set is, does it say, so of course not. Anyway, so this is data collected on 3 different types of penguins on certain islands in like Antarctica. We'll go back to the documentation, look at that in a second. But there's one called a chin strap penguin. I'm guessing that's because of this black strap around its chin area here. I don't know. I'm not a penguin expert. A Gen 2, is that a Linux variety penguin here? He's got the orange bill and the orange feet. And then Adelaide, I don't know. Again, I'm not a penguin expert, and I'm definitely not a pronunciation expert. But basically, our response variable here, I don't know why I said like our response variable here is going to be one of these 3 species of penguins. And we're going to try to predict that based on like physical characteristics, like how long their bill is, how deep their bill is. I think things like their height and their weight. Kind of an absurd thing, because I think, there's other ways to figure out what species it is rather than machine learning something based on their height. Like they're not going to send me to Antarctica and be like, weigh these penguins and then use that to classify them. They're going to, send a trained expert and do it. But it's fun, so we're going to do it. Right. So yeah, Palmer Station in Antarctica. Okay, cool. I guess before I even do anything with it, there's a question is, why are we using this data set? A lot of times people will go to this data set right away. They'll be like, hey, oh gosh, I hate that. The iris data set has 3 different species of flowers and some physical measurements. You might notice that these are like really similar data sets in that respect. So why not just use iris? Well, for a lot of reasons of varying degrees of severity depending on who you ask. So one long-standing reason not to use the iris data set is that it's boring. Like who cares about the physical measurements of these flowers? If you're a botanist, I'm sorry. Penguins are cuter than flowers. I'm sorry. That's one reason. Another reason is that for what we're about to do, which is classification, this data set is too easy. The classes are almost like fully separated, so you get super low misclassification rates and you can't illustrate things. There's another reason that has always existed, but has been spoken of a lot recently, and people have been bringing this up, which is the source of this data set is troubling. And you might be wondering, wait, how on earth could a data set about flowers be troubling? Let's have a look. If we go to the documentation, blah, blah, blah. Okay, blah, blah, blah. Species of flowers. Okay, whatever. It's measurements of flowers. Who cares? Well, this is why we care right here. So this guy, R.A. Fisher, who you cannot escape in statistics, he developed like, half of what we still use today. He developed it. He has a troubling past. So did a lot of his contemporaries who developed statistics. A lot of them were involved in the study of eugenics. So this data set was literally published once in a eugenics journal. So that's sort of sensitive if you think about it. Now, I'm not going to make any big sweeping claims here, but what I would like to note here is that the history of statistics is complicated. There was a lot of folks studying eugenics at the time. How they viewed the application of that, varies in degree from maybe they were just naive to, oh my gosh, this is the most evil thing you've ever heard. I'm not here to make those types of judgments because I don't know the history well enough. But if you're interested, reading about R.A. Fisher alone is very interesting because not only did he do a lot of foundational work in statistics, he also did a lot of foundational work in genetics and biology. And we use a lot of his stuff even to this day. And then if you're really interested, the interplay between him, Pearson, and then student, that is William Gassett of the Student's T-Test, it's an odd history, but none of them come out looking all that great. And it's something you should know about. So we have the statistics field, we have a questionable history, but yeah. So there's 3 reasons not to use the iris data set. Or you can just say, you know what, penguins are cooler than flowers, and then use that instead. Okay, so I don't need to talk about this anymore. All right, so what I want to do is plot the penguin data. Oh, wait, no, let's look at the penguin data more first. So what do we have here? We have the species, of which there's 3 that you saw the pretty pictures. The island, which the measurements were taken. Some physical characteristics like the length of their bill, so this way, the depth of their bill, this way, how long their flippers are. That would be their feet, I think, but I'm using my hand. Actually, I don't know. Are the flippers their feet or their hands? It was in the documentation. Their body mass, how much they weigh, their sex, and then the year it was measured. Okay. So what I have here are some plots of one variable against another. So here we have mass against flipper length. So right away we can see that whichever category the green one is, it's like, oh yeah, like we can, that should be easy to classify. And then red and black here, I forget which penguin it is, but I wouldn't know what the penguins mean anyway, so whatever. But you should use a legend. Too much overlap here. Maybe it's a little bit more black up here, maybe a little bit more red down here, but that's gonna be harder to classify. But if we also look at bill length versus flipper length, well, now black and red are pretty separated, as is green. So this should be a pretty easy classification. Let's have a look. So what I'm going to do is, I don't need to turn the, I'll leave that up. So I want to fit, let's see, just checking my notes real quick. Yeah. So I want to make a model for the penguins. and I'm going to use a tree, and it's this species variable that I want to predict, and I'm going to use all the physical characteristics and sex, but not year, just because I'm not too certain about that. I'm not test train splitting the data or anything, so let's just pretend that this is a training data set. And I'm going to use default parameters otherwise. Okay. Let's look at this. So our part dot plot penguin model. I want to use type 2 here, and then pardon me while I do this real quick. This is just to keep blacks with blacks and greens with greens and reds with reds, because for whatever reason the folks who did our part dot plot switched the order on one of them. But anyway, not super important. Oh, I do want to turn my device off so I get it all in one plot. Okay, so what do we see here? Okay, so nicely this creates a legend for me. That's useful. So we see there's one root node, 2 internal nodes. Hey, this is really similar. And then we see these 4 terminal nodes. So like down here, 44% of the data ends up here. 97% of which are these Adelaide, 3% which are the chin strap, and 0% with our the Gentoo. So that's doing pretty good. If we go, say, down the right end side, which is they have a flipper length that is greater than 207, and they're not on one of these 2 islands, well, then it's 100% Gentoo. So this was actually pretty easy to classify. There's a little bit of impurity down here, but there's only 2% of the data there, so no big deal. This is probably the hardest to classify thing. So 6% chin strap, 6% Adelaide, 92% chin strap, which if we go back to this picture here, so that was red and black being mixed up. We see red and black mixed up there. And there's some here, but taken all together and with the tree that we fit there, that's what we got. Okay. So the last thing I want to do is I want to repeat that process, except I'm going to call this penguin mod big. Change that there, and all I'm going to do is a min split of 2, and and a CP of 0. So when we did this for regression, this would have put each individual observation into its own terminal node. But let's see what happens. And when I run this, I would have been really upset because it would have taken forever to plot it, not to fit it. Let's see what happens here. Aha. We don't see all that big of a tree. And why is that? Let's see if I can make this big enough that we can see it. Okay, this might be pretty small, but so despite the fact that there were like 300 and some observations, we only end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 if I can count right. Well, we said min split of 2, so that means you can always split. And we said CP of 0, and that means that any improvement at all, and we'll accept the split. Why didn't we split more? Well, if I get really close to my monitor, it turns out that every single one of those nodes is pure at that point. So that means that we can create neighborhoods in the 8-dimensional space, wherever it is, that only contain one species of penguin. Now, that's with the training data. Now, if we've fit this model and had test train split it and then evaluate on held out data, I mean, I don't think we're going to get 100% accuracy or 0% misclassification, but I just did this to show, 1, you can perfectly separate things out, but 2, it'll stop splitting early if you get a pure node. I mean, you don't have to do that. You could split it more, but whoever implemented our part said, why split if it's already pure? It's not going to change anything. So there's that. Okay, cool. So, I think that was everything that I wanted to say. The main point I want to drive home is that, aside from being able to, make these new, somewhat different classification trees and estimate conditional probabilities in addition to making the classifications, everything we've seen here is pretty much just exactly what we did in regression, but ever so slightly different. So hopefully this week will feel easy and that like it's a bunch of new stuff, but it's so close to what we saw before. Okay, so as always, if you watched until the very end, good job, and I'll see you in the next video.